Hello, this is S&D College of Engineering and Research Center, Yeola. Lecture series for first year engineering physics. I, Dr. Chaudhary Vivek Sitaram from first year. Today's topic is about the diffraction. Now, as we know, diffraction means bending of light around the sharp edge of an obstacle and falling in a geometrical pattern. So this is nothing but the bending. So there are two types of bending. One is Fresnel bending and another one is Fraunhofer bending. In Fresnel bending, the object and the source having the finite distance. It means the source are not having the monochromatic and other light sources. Monochromatic, coherent is not there. So distance is finite, and if we are observing it from the spherical wavefront, that is wavefront point of view, it is having spherical, cylindrical and other types of wavefronts. It is not having the plane wavefront. But if we are observing Fraunhofer diffraction, there is a plane wavefront, means rays are parallel to each other, and that is nothing but the distance is infinite and all rays are parallel to each other. Coherent sources are generally considered. Now spreading diffraction is nothing but the spreading or bending of light waves as they pass through an aperture or round the edge of an obstacle to produce geometrical shadow region containing dark and bright bands is called the diffraction. Now, after diffraction, we are getting in Fraunhofer diffraction, just I had explained, there are parallel rays are observing and there is diffraction at an angle of theta. All rays are diffracted in both the directions. If we consider only one-sided, then by using bioconvex lens, these rays again converge at a single point. So if we are observing this Fraunhofer diffraction by a single slit, and slit is having the width dx for infinitesimally small slit is we are considering. Now, as we are considering the main slit, it is divided into the small slits, divided into n number of slits. So dx plus dx n times. That's why it is the dx. So there are two rays. If we consider two rays, so first ray is diffracted over here as a ray 1 and other over here is ray 2 is diffracted from this. Both the input rays are parallel, so at the after diffraction we are getting parallel rays and both are having the same theta direction. The path difference between the first ray diffracted first here at an angle theta initially, second ray also diffracted at an angle theta, but the path difference between these two rays is nothing but 2 pi by lambda into dx sin theta. So, and according to that, phase difference is equal to 2 pi by lambda into a sin theta. So here if we are observing the distribution, resultant amplitude of the wave distributing arriving at the point, so there is a phasor diagram distribution of the amplitude points and the angle. And from this, the resultant amplitude distribution over here in this diagram, if we are observing it, so here is the maximum amplitude distribution, E theta is the resultant amplitude and phi by 2 is the angle between two radius of curvature. So by the numerical mathematical calculations, as we know, this angle is phi and it is divided into phi by 2. As we know, angle is equal to arc upon radius, the length of the arc and length of the radius, and from that, after that we come to know E theta is equal to em sin of alpha upon alpha, where alpha is equal to phi by 2. So here the theta, now from the geometrical we come to know E theta is equal to, for principal maxima. Now, what is the condition for principal maxima? The phase difference should be 0 and the path difference should be multiple of lambda. So that's why here we get the, according to this, the distribution of maximum amplitude distribution. So maximum possible amplitude when sin alpha upon alpha is equal to 1, so we are getting the maximum amplitude, and this will happen when alpha is equal to 0. When pi by lambda a sin theta is equal to 0, and this is only occur at the theta is equal to 0, and that's why exactly at the center we always get the maxima. Now condition for minimum. So first minimum we are observing over here, alpha is equal to at m pi plus minus m pi, where m is equal to 1, 2, 3. And now from this we come to know the between the two main minima, secondary minima is present. That is the condition alpha is equal to plus minus 2 m plus 1/2 into pi. So here first maxima we will observe over here, and the first minima is observed here. Then again second minima. So according to the first minima over here, minimum 1. So here if we put the different values, we will get over here. So if we are observed in the diffraction pattern, exactly at the center we are getting the maxima here, then minima, then dark band, then again bright band, then again dark band, then again bright band, dark band, bright band alternately. But remember this thing that the intensity is maximum at the center and it is decreasing continuously towards the periphery. And this is nothing but the Fraunhofer diffraction due to single slit. And if we are observing number of slits are drawn on a glass plate by a very small distance, then that element is called as a diffraction grating element. And the grating element is given by the distance between transparent line and opaque line. So it is a plus b is equal to 1 upon n centimeters. So as we know, diffraction due to single slit. Now if there are number of slits are parallel to each other, what will happen? That is given by over here. So E theta is equal to Em into sin alpha upon alpha, that is for the single slits. For n number of slits, it is multiplied by a plus b. So we are getting the phase difference twice beta. Now if we observe the distribution pattern, that is diffraction pattern. So due to single slit, we are getting first maxima, another one, again maxima, and in between these two maximas there are distribution of minimas. So this is nothing but the diffraction pattern due to n parallel slits. Thank you very much.